next task is to come to scalars. What are scalars? Scalars are simply numbers. So it's all the things which describe just one value, and we want to be able to compute with them, to count, etc. So there is a list here on the board: natural numbers, integers, rational numbers, real numbers. Perhaps you also know complex numbers, reminder classes. I will just tell what they should be about, but it's all easy because they are simply gadgets which satisfy the rules which we expect from computations, right? So there is the addition, there is the multiplication, and we want that there are the properties we expect, right? So it doesn't matter in which order we add or multiply things, and there is this distributivity laws and things like that. So for example, distributivity is this one, right? So it doesn't matter in which order we multiply and add in this sense, etc. I will not go through, you can read yourself, but it's clear that most of the rules are satisfied by all the guys here in my list, right? So the natural numbers would be for us mostly starting with 0, so they are like this. Then there are the integers which have additionally also the negative values of the same ones, etc. Then you have the rationals which are obtained as quotients of the integers, and q must not be 0. Real is something like a real line, so where we fill the gaps, as we shall see soon, left between the rational numbers. And complex numbers are a bit more complicated. So what about the complex numbers? So we want to be, if we come to the complex numbers, so it means that we would like to be able to compute with things like, well, there's the complex numbers. So they should look like a plus I times b, where this I is a special number which we declare to be our choice to fulfill the equation a squared is minus 1, which normally among the real numbers is not possible to fulfill. But as soon as we add it, it's easy to see that if we just write a plus ib and multiply it with c plus id, and we request that all the rules here you see, so all these things should be still valid, I mean all these axioms, then there is a unique way how to define the multiplication and addition. And the addition is simply by components. Multiplication is a little bit more complicated, but that's not a building power, nuclear power plant business, right? So it's pretty easy. Another option how to see it is you can simply imagine the couples of the real numbers are positions in planes. So we would have the origin here. So there's the 0, here is the real line, here is 1, here is minus 1. And then you can imagine that the operation there is defined in such a way that we add the number as we are used to be adding vectors. So if we have one vector and the other vector, then we know how to add them. We get this one, right? So that's the result. If we want to see how to multiply the numbers, then, well, there are not so many options which would sound naturally, but what we definitely can do is just to see what's the difference, what's the distance of the points from the origin in the Euclidean natural way, and we multiply the distance. So having these two, so if they are smaller than 1, then it would be something smaller together, so it could be something like lying on such a circle. And then what we do is we look at the angles and we add the angles, and then you see immediately that if we expect that this could be the right operation for multiplication, just multiplying the distances and adding the angles measured from the real line, from the number 1, then clearly the I must be here, right? Because that's 90 degrees. And if we if we make the square of I, then it must be just adding 90 degrees twice, and then we come here, and the magnitude of I will be 1, and therefore that's what we exactly expect. So that's the complex numbers. But what were so if I go back here, so what were the remainder classes? There it's even more easy, because there we simply do the integer arithmetics, this one, and we are simply in the end of our computation, we are interested only what's the remainder when dividing by k. So if k equals 2, then it's extremely easy, because the z2 will be just having only two elements, 0 and 1, and they tell us simply whether the result of our computation is odd, that's the 1, or even, that's the 0, and everything works. Again, you can easily have a look that all the properties will hold true. But what about if you look at the natural numbers themselves? So the natural numbers, so that will be now this question mark, which I am most interested in, because, well, for some of you, you can just stop listening, but for those who are bored so far because you haven't heard anything new, maybe now you will. You can imagine that you have got the natural numbers, but I will define the plus and times a different way. So I will say that, let's say a plus, so I will write it this way, b equals the maximum of a and b, and I will say that a times b is simply a plus b. So that's the ordinary plus on natural numbers, right? And the natural numbers start with 0. So you see, if you go through the list of the rules, then nearly everything will hold true, right? Except we shall have troubles with the existence of the inverse at the addition. There is still the neutral element 0, because that's the 0 still, because if I take maximum of anything with 0, then it's this anything. And this is a very strange operation, right? You see, because if I take a plus a, in this sense, this plus, this plus, then it's again a. So that's something we call idempotent. It's not forbidden in our rules. So these are very strange scalars, which are the basics of what the people call tropical algebra. And actually, it's more common to use them in another way, because it's easier to see them in a way that you would take all the r, but you add to the r minus infinity. Yeah, and then a plus the new plus b will be maximum of a and b. And in this way, the minus infinity plays the role of 0, right? But a times b is simply a plus b. And here it's already nice, so we could have done the same with integers. Here we have got even the inverses for multiplications are there. So this is what the people in the tropical algebra call semi-fields. In general, it's called semi-rings, whereas here we talked only about commutative rings. And that's a pretty important object, because as you may imagine in data science, the maxima and minima are very often used in some discussion about the data. And so this kind of algebra is very helpful. So you might meet that after some time. So that's about the scalars. But what about the functions? Functions are simply some rules which assign to some arguments some values. So that's exactly what we work with, because you have some, say, items in your population and you know a lot of parameters about them, and having a look at one of them means you are observing a function. If the number of arguments is finite, then you can have the function given as as a table. So that's the easiest way. But you can also on real numbers, so for example, a scalar valued function on real numbers can be given as a polynomial, because we know what the multiplication is. It's 3 times the argument plus something, and it could be of any order. So there might be 7x squares and so on. So that's a very easy way how to understand a function. But you could also, as we shall see soon, you could define the value by some limiting procedure. So actually the expression will be infinite. So you can't compute it really, but you can tell a lot about the value and the properties, etc. And even more difficult is to view a function, or at the same time much more common, to view a function where you simply know how the value of the function changes if you change the argument. And the easiest way how to understand it are the so-called recurrence equations or difference equations, and that's what we shall be looking at now. The last thing is even more complicated, because, for example, if I say that a well-defined function is after how many days each of us will be dying, then it's a well-defined function. So there is some fixed number of days left for us, but no one can compute it, right? But if I know how much you drink, what you are smoking, etc., and how is your way of driving, one can make some estimates. And if it's made for a whole population, for insurance companies, it's good enough, right? And that's what the inference, the statistics is about. And that's the absolute basis of data science, right? So we shall come to that task, which is much more difficult later. But for today, let's focus on the difference equations. And the difference equations are, so the easiest one, so the simplest one is the equations of first order, right? So you can imagine that you simply know how your function small f will be valued in n plus 1 if you know what is the function in n, and there is some expression for that. So, for example, the absolutely simple one is this one, right? So that's the linear difference equation of first order with constant coefficients, right? So of course you can do that over each of the scalars, so even the tropical ones, and this will have some behavior, but assume we are over reals. So over reals this will be quite simple, and actually this is exactly what you need to compute how long you will be repaying a car, or how much you save if you just add b to your account each unit of time, and a is reflecting the interest rate, right? So this is a very, very useful thing. You can read through and find out some first glimpses into, say, mathematical theorems which look awful but are simple. But let's have a look at a model which is easier, and then it's equipped with my favorite emoticon. So for some of you, this should be read clearly as just stop now and skip this, because we don't want to frustrate anybody. But for others, it will be meaning finally something interesting, right? So imagine that we have got a dependence where actually the population can't grow in the like in this exponential way all the time, but we want to see that the change of the growth, so that's this delta of p is the change between the n's and n plus 1s, and the proportion of the change to the absolute value where we are, so that the relative growth should be linearly dependent and should be having the feature that if p is small, then it grows with some constant rate, like the interest in the bank exponentially. But if we are approaching some limiting value k, then it doesn't grow at all. And the difference between them should be linear. So you see, the only way how to get there is that if p is 0, then so that's the general expression for linear dependence between y and p. And if the p is 0, you see that that the growth is by r, which we wanted. And if the p is k, then you see that there will be plus r minus r, so it's 0. So it's what we wanted. And this is the so-called logistic model. If you rewrite it, so this is the delta of p, we divide it by p, and this is what we had here on the right hand side, and then we recompute it, and we see what's the difference equation. So that the recurrence will tell us how the growth will be. And this is something which, for example, can be easily applied for very simple modeling of, say, population growth or infectious diseases spreading, etc. And I have prepared earlier already. I have prepared a example how this works. So you see, I now clicked into the interactive syllabus, which is at your disposal, so you can do exactly the same. I just copy it and I will throw it into the Sage cell because it's a Sage code. So if I do it, so I will explain what's there, and you see this interact in the beginning means that the whole thing is considered as a procedure which is displaying something interactively. And the first line tells about the parameters which are there. So it's all saying where from, where to, and what is the step. And now what the parameters say is, okay, is the number of vulnerable people in the population. So I was working on that when the COVID was, well, I was trying to reflect what a simple model for the COVID spreading in Czech Republic. So K was something between 0 and 10 millions, and I'm counting in thousands. So therefore you see it's just what's here. So from 1 million to 10 million, jumping by 500,000. So the small r is the ratio how quickly, so what's the rate of getting infected if you meet someone. P is the starting point, n is the number of iteration, and phi and psi are interesting because phi means if you finally end in hospital, well, how many of the infected one end in hospital, and psi is how many of those in hospital will land an intensive station. And if you evaluate it, you can look at the code. It's extremely simple, so there is nothing complicated to discuss, but let's work a little bit with the parameters, right? So say something like 0.15, the growth as 15% is about what would be expected with a flu. Say 1/4 of the population is vulnerable. We should start with something bigger just to start with, right? So say we had something like 100, well, I say 50,000, 50. That's the number of iteration. I have to go on just to see the result because it's going slowly. And here with the flu, perhaps, I don't know, 1 of 70 will end in hospital, and maybe 1 of 5, no, 1 of say 20 from them would be in the intensive station. So you see the result that this is the way how the epidemic would go through in our very simple model. And you see that the peak in the hospital will be not very horrible. It will be just 4,000 people with the flu, which means it will be mainly people who are sick another way, but they were hit by the flu and therefore got worse, and they landed in hospital. And some of them were very bad, so you will have 200 of them at the intensive station, right? Whereas if we view what was happening with the COVID, so there before the measures were taken, it was much higher than this. So the number of vulnerable was nearly everybody was vulnerable, say three quarters. So even if we started with very little, so it was just growing fast. I don't need to iterate that long because there is no way to go, right? And of course here it's also much worse because say 1 of 20 would go to hospital and 1 of 10 there would be then going to the intensive station, and you see immediately that there are absolutely horrible numbers. And then there was a political way how to approach, how to decrease the communication, right? So for example, by decreasing the meetings of the people, you could go down with R, which just makes it much easier, right? Was vaccination, you could just decrease the number of the population who are vulnerable. This early early healing and proper approach, you can simply diminish the number of the people who end in hospital, and you can make it even nicer here, right? So, and then of course you end up with much better numbers, which was roughly the case. So this is a simple say motivation or initiation. I was much slower than I intended, so sorry for that, and I hope you will at least enjoy. Have a nice day.